Go. Okay, so today we're talking about the integrated rate laws. Last time we talked about method of initial rates, where I give you a whole bunch of data, right? I gave you a whole bunch of data and I told you, okay, this is reaction number 1, this is trial number 2, this is trial number 3. I gave you concentrations and rates, right? That's what we did last time. And you figured out the rate law based on initial concentrations, right? Hence the name method of initial rates. And then I said, okay, well, we're doing this at the very beginning, and then next time we'll figure out concentrations at some point in the future, or the rate constant at some point in the future, right? That's what the integrated rate law allows us to do. Method of initial rates is to figure out the rate law at the very, very beginning, because remember, reactions are slowing down over time. And so now we can figure out what's that concentration going to be 20 minutes down the line. Or how long is it going to take to get to a certain concentration? Or what's the rate constant going to be 3 hours in, right? So that's what we're doing today, the integrated rate law. Now we're going to do a little bit of math review, natural log review. So if it's been a while since Algebra 2, or I think it's covered Algebra 2, college algebra, right? Let's review math, because the integrated rate laws do involve solving equations where natural logs are part of the formula. Okay, so a natural log, ln, is just logarithm-based e, that's Euler's number, okay? And so just like to get rid of log base 10, you raise both sides to the 10, right? If you want to get rid of a regular log of 10, a log base 10, you raise both sides to the 10. To get rid of a natural log, you raise both sides to the e, okay? So for instance, if I said to you, okay, natural log of x equals 5, what's x? Well, how do you undo a natural log? You raise both sides to the e, okay? Just like if this said log x, if it said log x, how would you get rid of the log? You'd raise both sides to the 10. How do you get rid of a natural log? You raise both sides to the e. So e to the ln, well, that cancels out. So that means x is equal to e to the 5th, right? Because e to the ln, that's like tying a shoe and then untying it. That undoes each other. So in your calculator, you should have a button, e to the x. On mine, it's second ln. So on my calculator, to enter e to the 5th, I would say 5 second ln, and that gives me my answer, 148.41315, blah, 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 which I would then round to the correct number of sig figs. So make sure you can do this on your calculator. Now, if you have a big number right here, like let's pretend this is 900. Your calculator may not be able to handle a number that big. E to the 900 is an actual number. You could leave it like that. So if your calculator can't process a number that big, e to the 900 for instance, you could just leave it as e to the 900. Just like pi is an actual number, right? 3 pi over 4, that's an actual number. You could leave it like that. You don't have to put it into a decimal. So if your calculator can't handle e to the 900, you could just leave it as e to the 900. But most calculators can even handle that. I think even my dainty old calculator can handle e to the 900. Nope, it can't. Sorry, just kidding. Some of your graphing calculators can handle those though. All right, so try this one. I'll pause the video just to make sure that we're good. This has got a little bit more algebra in it. See if you can solve for z in this equation. I'll pause the recording for a second. Okay, let's see if you got it right. Doing some algebra. Natural log of z plus 3 equals 0.4. So first thing we have to do before we can do anything with this parentheses business is we have to get rid of this natural log, right? So how do we get rid of the natural log piece? We raise both sides to the e, right? Euler's number. So e to the natural log of z plus 3 is equal to e to the 0.4. Well, that's a number you can enter into your calculator. E to the 0.4 is a number. So 0.4 second ln, that is a real number, 1.49182, blah, 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 blah. All right, so e to the ln, that goes away. So you're left with z plus 3 is equal to 1.49, right? And then solve for z, I should say. Do we agree on how to do this? Just using a natural log, maybe something that's been a while since you've had to do. So I always want to refresh on some of those topics that you may not have to use every day. Everybody good on natural logs and how to get rid of them, how to make them go away? Okay, let's talk about first order reactions. So these are reactions involving a single reactant. Some reactant A is decomposing into products. How many of you are calculus students? How many of you are taking calculus or had calculus in the past? All right, that's like everyone in the room. Great. So if we're thinking back to calculus, you know, you sat through calculus and you're like, when am I ever going to use this stuff? Can't believe I have to do this. Blah, blah, blah. This is a real world application of calculus. I'm so excited to have everybody in here be calculus students. All right, if you look at this equation right here, right, the rate here is just the derivative at time t, some point in the future, right? That's just the derivative with respect to time, yes? So what we're doing essentially, this is why I say calculus-based physics is so much better than algebra-based physics, because if calculus-based physics, you just take the derivative. Bada bing, you're done. You don't have to deal with all those equations you have to have memorized for non-calculus physics. Well, that's what we're doing here. We're just taking the derivative at that point. All right, so rate is equal to K times concentration of A to the first. We don't have to write that 1 if it's first order, right? But that's how we knew it was first order too. We could know it's first order just by looking at the rate law, right? K times A, and that's first order. All right, now let's do some calculus. Yes. Just FYI, you don't have to do calculus on the test, but I like to show you where this stuff comes from, especially since you've had it, right? So if you hated calculus and you still have nightmares about it, just cover your ears for me. So you're not going to have to derive this, but I like to show you. I mean, it's called the integrated rate law. So what do you think we're going to do? We're going to integrate, right? So if this is first order reaction, right? Rate is equal to K times A to the first, right? With respect to time, we're just going to integrate both sides from initial concentration to some concentration in the future, from 0 to some time, right? And we're going to use our integration rules. So we use our integration rules, and this is what we get. That's the product of our integration. Wow, that's the integrated rate law. That's where it comes from, okay? So if you've ever wondered, where am I going to use calculus? This is where it comes from, integrated rate law. So that's as much calculus as you're going to have to do. I will give you this formula on your reference page. You just need to be able to use it, okay? Is that fair? So the natural log of A, initial concentration over A at some point in the future, is equal to K times T. So ln is just natural log, right? It's capital Ln on most calculators. A is concentration of whatever A is at some time in the future, T. T stands for time, K is the rate constant, and A sub 0 is the initial concentration, right? This is how much we began with. This is how much we have left at some point in the future. You would expect A to be greater than or less than the initial. What's going to happen to A with time? Is it going to go up or go down? It should be decreasing, right? Because the amount of reactant is going to go down over time. One thing to make a note to yourself, okay? Put this in your notes. If you're doing some sort of calculation, make sure that the unit of time in the rate constant and the unit of time in the future match, okay? Because if the rate constant is in moles per liter second, and I ask you about some point 3 hours in the future, this is in seconds, this is in hours, you're going to have a clash. So make sure the unit of time in K matches the unit of time in the future, because otherwise we're going to have problems in terms of our units. Okay, make sure that those two units match each other. The unit of time, minutes, hours, decades, millennia, whatever, needs to match the unit of time that's in the rate constant. Otherwise, those two won't be compatible with each other. Because ultimately, you're going to want time to cancel out. Does everybody understand how the variables work? Right? I won't make you derive it. I'll give it to you on your reference page. You just need to be able to use it. Now, we can also use this to solve for any of the variables, right? We can solve for concentration. We can solve for the rate constant. We can solve for how long it'll take, right? We can solve for any of these variables now. Now, we can rearrange this into slope-intercept form. We're going to do some graphical analysis today, and you're going to do that in lab this week as part of your assignment for post-lab. So if we rearrange this into slope-intercept form, here's what it looks like in y equals mx plus b. Y equals mx plus b. Right? So when we do graphical analysis, if you plot natural log of concentration versus time, and it's first order, it should be a linear line, and the slope of that line is the rate constant. So this week in lab, you're going to do an experiment. It's a really classic experiment. You're going to collect a bunch of data, and you're going to determine, is it zero order, first order, or second order using graphical analysis. And based on your R-squared value and the slope of that line, you can determine which order the reaction is. You can get the rate constant. This will be given to you as well on the reference page. So I'll give you both versions. You can pick either one, whichever you're more comfortable using. Okay, if you don't like dealing with this fraction, if that fraction scares you and freaks you out, use this version. Okay, they're the same thing. This is just rearranged. So if you plot time versus natural log, the slope will be negative k. We're going to see this today. I'm going to go through some sample data. So this is how you can confirm that your reaction is first order. Again, I'll give you both versions on your reference page. You just need to be able to do the arithmetic. All right, so why don't you try this one? I'll pause the video. Here's the reaction that we're studying. If the rate constant for this first order reaction is 6.93 times 10 to the negative third seconds inverse, and the initial concentration is 0.1 molar, what is the concentration after 150 seconds have elapsed? I'll pause the video, give you a second to try, and then we'll go. All right, let's go over this one. So we know it's first order. I told you it's first order, right? So we're using the first order integrated rate law, and you can use either version, whichever version you're more comfortable solving mathematically, makes no difference to me. And we're just plugging in our values, right? This is K. This is the one with the 0 next to it, right? That's initial concentration. This is time, and we're solving for A in the future. Now my units of time match, so we're good here. If this were in minutes inverse, but this was in seconds, I'd obviously have to convert seconds to minutes, right? Make sure that you make the units of time that you're solving for match the unit in the rate constant, okay? Because otherwise you'll have a funky answer. So now we're just plugging in and doing the algebra, right? I picked this version, but you could have picked the other version. It's going to work the same either way. So rate constant gets plugged in. This negative is part of the equation. It's built in, okay? And there's the time. So seconds inverse and seconds, they cancel. And then natural log of 0.1 gives me this, right? Plus a negative, that's where that negative came from, because this is a negative number, plus a negative. There's this number, just carried straight down. And so now we say natural log of N205 is equal to negative 3.343. How do I get rid of that natural log? I raise both sides to the E. E to the ln cancels. So that means that the concentration is E to the negative 3.343. My answer needs to be rounded to 3 significant figures, 3, 3, and 3. So 3 sig figs here. And don't forget, because this is concentration, it needs units. Units would be moles per liter. Also ask yourself if your answer makes sense. We started out with a concentration of 0.1, so is 0.0353 reasonable? Yes. If your concentration went up, would that be reasonable? No, it would, because remember, these are reactants. Reactant concentration is going to go down with time. Product concentration would be going up. Okay? Does this make sense? If you made a mistake, do you see where you made it? You're feeling okay about plugging into this equation? Yes? I've got some practice problems I'm going to give you at the end of class for you to do on your own time, and the answer keys and a video on it. It's all going to be posted as well. Okay, this is what I just said. Unit of time's got to match, absolutely has to match, right? If this was in minutes inverse and this was in hours, we have to make this either convert this quantity to minutes, convert this quantity to hours inverse, or convert this quantity into minutes. Either one, you got to match, okay? So try another one, just to make sure you're good at this. First order reaction, generic A, B, decomposing into A and B. Rate constant determined to be 5.43 times 10 to the negative third seconds inverse. If the initial concentration is 3.5 molar, what's the concentration after 200 seconds? Take a minute and try this one. Okay, let's go over this one. Again, it's still first order, so we're using the first order integrated rate law. So those are the variables that we were given in the problem. We know the rate constant, we know the initial concentration, we know how much time has gone by, and we want to know what's the concentration after those 200 seconds. So plugging in, right, natural log of AB is equal to K, negatives built into the problem, times time, plus the natural log of the concentration initially. Right, so we do some reduction, natural log of concentration. How do I get rid of that natural log? E to the natural log undoes it. So E to the 0.16676, rounding my final answer to three significant figures, 1.18 molar. Does that make sense? Did the concentration go down? It did. Did you get it right? Did you get it right? If you made a mistake, you see where you made it. Okay, because that's the most important thing. Okay, now half-life is something you hear and you usually think about radiation, right? Half-life, well, that is true. It does apply to radiation. And actually, at the end of the semester, when we study nuclear chemistry, we're going to come back to this exact formula. But half-life also uses a lot of applicability in the medical field, right? If you have a drug, what's the half-life of that drug? How long does it take that drug's concentration to go down by half? That's what we're talking about by half-life. Okay, half-life is a unit of time. It's the time it takes the concentration to go down by half. And again, you see this a lot in the medical field, right? If you're studying some sort of drug from a pharmacology standpoint, how long does it take half that concentration of the drug to go down, right? It's a unit as time. So natural log of 2 over K, if it's first order. Obviously, it'll be different if it's second order or zero order. So half-life for a first order reactant is natural log of 2 over the rate constant. And again, this is a unit of time, right? So this is a unitless quantity. This would be seconds inverse or hours inverse or minutes inverse or whatever. So 1 over minutes, right? That means that this is going to have units of minutes or whatever the units of K time are. Okay? Now again, I'll give you this on your reference page. You'll just need to be able to do the math. So why don't you try this one? A certain first order reaction has a half-life of 20 minutes. What's the rate constant for this reaction? I'll pause the recording and give you a second to try that. Okay, these are a lot easier, right? Natural log of 2 over K. So you're just solving for K this time, right? And I tell you that its half-life is 20 minutes, so that means that K needs to have units of minutes inverse. Do we agree? Did you get it right? Natural log of 2 is just a number, right? So you can enter that in your calculator as ln2 in parentheses and leave it like that. You don't have to round it, unless you want to. You don't need to. Did you get it right? If you made a mistake, you see where you made it? Everybody good on this one? All right, now let's move on to second order. So we're still looking at one reactant, breaking down into products. So we're looking at the derivative again. So rate is equal to K times some initial concentration to the second this time. Right? We're going to derive it. Again, we don't have to on a test, but just so you have an appreciation of where it comes from. Since this is the integrated rate law, right, we're going to integrate, right? So rate is equal to K times A to the second. Right, we can rearrange this. We're just doing some rearranging. And then we're going to integrate from initial concentration to concentration in the future, from 0 to some time t. What's the product of integration going to be here? If you remember your integration rules, right? This is what we'll get when we do our product of integration, and then we could rearrange that. Right, we're plugging in our 0 in our final and our 0 in our final. That's where that's coming from. That's what we get. So there's the second order integration rate law. That's all you need to know. I will even give you that formula, right? I'll give you the formula. You just need to be able to use it. And then there's half-life for a second order reaction. I should say second order reaction. There we go. So again, the integrated rate law and half-life equation will be given to you on your reference page. You just need to do the arithmetic. Obviously, if you wanted to derive it for yourself every time because it's fun, you could, but it's not necessary for the test. This isn't a calculus class, this is chemistry class. But it's always nice to apply that stuff, right? When am I ever going to use this? Well, I can think of at least one example. All right, so the math is no worse for second order than it is for first order, okay? So again, here's the summary of the two, first order versus second order, and the half-life equations. Now, what if it's zero order? Well, if it's zero order, then that means that the concentration of the reactant isn't factoring into the rate law at all. So in other words, rate equals K, right? That's all it is, rate equals K. So a zero order, there's what it looks like for an integrated rate law for zero order, and here's half-life for zero order. Again, I will give these to you. You just need to be able to do the arithmetic. Reaction. Is everyone good? Good, good, good. Okay, now this is something you need to know. You're going to need to know this for lab tomorrow and how you analyze that. It's also going to be on the homework this week. It's going to be on the test, all right? So make a note to yourself. This is something you need to know. How do I determine the order? I shouldn't say determining if a rate law, determining reaction order. There we go. Determining reaction order. First order, second order, zero order. You can do that by graphical analysis. And again, you need to know this. If natural log versus time gives you a straight line, then it must be first order, and K is just negative of the slope. Okay? If natural log versus time. Because think about what you have to do to a first order integrated rate law to put it into slope-intercept form, right? It's natural log as y and time as x, right? So if you're plotting natural log versus time and you get a straight line, it must be first order. That's how you would know graphically that it's first order. If you plot 1 over concentration versus time and get a straight line, then it must be second order. So let's pretend you plot natural log versus time and you get something parabolic. That's just a mess. Okay, well, it must not be first order. Let's try the test to see if it's second order. 1 over concentration, right? Think about the second order integrated rate law. It's 1 over concentration as the y component, right? So concentration, 1 over concentration versus time. If that gives you a straight line, then that means, hey, this is a second order reaction. And that means K is equal to slope. What do you think you'd have to plot to see if it's zero order? Just by looking at your zero order integrated rate law. What do you think you plot there? Something versus time, what would it be? Natural log of concentration was first order. 1 over concentration, so what is it? It's just concentration versus time, right? It's just straight up concentration versus time. If concentration versus time gives you a straight line, then it's a zero order reaction. So how do you know what to graph? Well, just look at your integrated rate law formulas, right? Integrated rate law for first order is natural log. Integrated rate law for second order is 1 over concentration. Integrated rate law for zero order is just concentration. There's no natural log, there's no 1 over, it's just straight up. Okay? This is something you need to know. And on the problems that I'm going to give you to work on for practice, obviously it's not for a grade, I'll state in the problem, you study a reaction and a plot of concentration versus time yields a straight line. What is the order of reaction? It must be zero order, right? Okay, so that's the kind of thing that you might be seeing in the future. I don't know why that didn't show up. K equals slope. All right, so let's do this one together. Here are some data. Okay, so I'm studying some reaction. I think I've actually put it in the slide here. Yeah, there we go. So this is similar to what you're going to do in lab tomorrow. You're going to, now this is obviously not, you're not going to be measuring in hours tomorrow. You'll be measuring in seconds. But you've got you've got concentrations versus time, right? As time is elapsing, what's happening to concentration, right? So you're going to collect data just like this tomorrow in lab. You're going to be measuring concentration, you're measuring time, and then you're going to figure out, is this reaction zero order, first order, or second order? Okay, so this is exactly the procedure that you would do as well. And by the way, there's a video on the website of just this. So if you don't want to watch the entire lecture again just to see this part, you could just watch the little video. So we're going to test for zero order, we're going to test for first order, and we're going to test for second order. Also, your lab manual gives explicit instructions on how to do this as well using Excel. All right, so here's concentration versus time. This is test for zero order, right? Because for zero order, I don't have to do anything. It's just concentration versus time. So I select my data, go to charts, nice smooth. Okay, now I want to add my trend line. Just right click, linear. I want the equation because that'll give me the slope, and I want r squared. All right, now I'd change my titles and axes and all that stuff. All right, so r squared is 0.998. That's pretty good, right? I mean, because what number do we want r squared to be close to? 1. All right, so this is zero order test. And then you can go to format, add chart element, axis titles, horizontal. So what are we plotting here? This is time, right? And this is in hours. Oop, not junior. Hour. And then this is concentration, moles per liter. All right, so I'm not going to do that every single time, but that's what I would expect your graph to look like at minimum when you turn it in. Okay, I want chart title, I want axis labels, I want to know r squared, I want to know your equation. Okay. So now let's do first order. So what am I doing here? Time is still the same, right? That's still the same. So copy, paste. Everyone knows how to copy and paste, right? Control C and Control V. Or on a Mac, it's the Apple C and Apple V. Now here we want natural log. Do you remember how to enter a formula? You just type in enter equals ln, open parentheses, select the number you're interested in, close parentheses, enter. And now, if you grab that little plus sign and just drag, it applies the formula to everybody else. So it's applied natural log to all these values. So this is test to see if it's first order. So again, we're going to highlight, insert, nice smooth line. And now we want trend line, linear, equation, and r squared. First order test. And then I would assume you know how to add these axes titles, right? We just did that a second ago. Here, what's r squared? R squared equals 1. Well, that's pretty good. Oops, wrote it in the wrong spot. R squared equals 1. All right, but I'm not done yet. I mean, you can't get any better than 1, but let's just make sure. Let's just make sure. So we're going to copy again. Now, to enter this one, equals parentheses 1 over, there's my number, close parentheses. Okay, and now select that cell, drag it down. There's everything else. Select, insert, smooth line, move it out of the way. All right, add trend line, linear equation in r squared. Move it where I can see it. Second, oops. R squared is equal to 0.998. All right, so now I can quantitatively, with confidence, say, yes, this is what order? 0 order, first order, or second order? How do I pick which one's the winner? What do I look at? The r squared, right? Because the closer my r squared is to 1, the better my line is fitting to the data, right? So this is a first order reaction, right? And so I would say, okay, what is the rate constant? How do I get that? We look at our trend line, right? And what specifically of the trend line do I look at? This is the intercept. That's not useful to me. It's the negative slope, right? So it's the negative of that slope, whatever that value is. Okay, so it's the negative of the value in front of x. So you're going to have to do this in lab when you're analyzing your data. You're going to make a graph for 0 order, for first order, for second order. I want to see all of your trend lines on your graph. I want to see your r squared values. So you're going to print those out and turn those in. Now, if you want to put all 3 of them on the same page, save space, that's fine, as long as it's big enough that I can read it. Okay. If you want to make a full page printout of each graph, that's fine too, but I want to see your graphs, the r squareds and the trend lines and all that great stuff. Any questions on using Excel to determine order of a reaction? Okay. So I think I've got a couple of problems in here that are just for practice. Thought I did. Okay, there's one. It's like, I know I had a practice problem in here. So you do this one. Well, we just determined that it is first order. Okay. So for a first order reaction, the initial concentration is that. Determine the concentration of the reactant after 2.7 times 10 to the 4th seconds have elapsed. Oh, and you need the rate constant. There you go. For a first order reaction, the initial concentration is 0.5 molar and the rate constant is 2 times 10 to the -4 liters per mole second. Determine the concentration of the reactant after 2 times 10 to the 4th seconds have elapsed. I'll pause the video. All right, let's go over the answer. So we're told it's first order, we're given the initial concentration and the rate constant, and we want to know how much we'll have after this amount of time has gone by. Does my unit of time match the rate constant? It does. All right, seconds and seconds, so I'm good. But always check that before you do any arithmetic, because if one's in minutes and one's in centuries, right, you're going to have a problem. So I got 0.14 moles per liter. Did you? Rounding to 2 sig figs. Oh, that's second order. Doggone it. I use the second order integrated rate law. So what do you get if you do it with a first order integrated rate law? I'll go back and change my problem for next semester for a second order. So what do you get if you use a first order? What do you come up with? We'll just do it by consensus. Anyone want to share? It should be in a similar neighborhood. It's a number less than 0.5 and greater than 0, so what'd you get? Do I need to work it out? 0.0023? 0.0023? Are you getting some consensus in the back? 0.002? Somewhere in that neighborhood? Yes? All right, we'll just go with that. Okay, so now I know for next time I use these slides. Do you want me to go over it on board, or are you good? You good? Okay. All right, then. Well, then we will stop.